All right. Hello. Thanks for having me. Yeah, I work for the LIGO collaboration, which is sort of jointly run out of Caltech and MIT. And I'm going to start by talking about a little bit about what we do and how the LIGO detectors work. Just what's been planned is some computer simulations of black holes colliding with each other, which are our primary sources. So these are all simulations of gravitational wave detection events that we've had so far. So these are the two black holes orbiting around each other, and this is the signal they emit that we detect with our detectors. And I'll talk a little bit more about that. All right. So what are gravitational waves? So Einstein is most famous for his general theory of relativity, which was a new theory of gravity that was trying to kind of fix some things some sort of mysterious new things that they had discovered about mechanics. And his theory predicted that there should be waves of gravity. And at the time when he made the prediction, this was in basically 1916, they thought that these waves would basically be impossible to detect because they would be so weak. And so basically 100 years later, we finally got to the point where technology had caught up and we were able to detect these things, so we started to build some detectors. In the 90s, some guys actually won the Nobel Prize for showing that something was emitting gravitational waves, even though we didn't detect the gravitational waves directly. But this was a really big discovery, and these guys got the Nobel Prize in physics for just predicting that the dynamics of these two stars that were orbiting around each other was consistent with them losing energy because they were emitting gravitational waves. So any sort of wave carries energy with it. So if you have a system of masses moving around and they're emitting gravitational waves, then those gravitational waves are actually taking energy away from the system, which causes the dynamics of the two orbiting bodies to change. And that's what this is showing, is that like over time, the rate at which these two bodies are orbiting around each other was getting faster and faster. And the dots are the observation. The line is the prediction from Einstein's general theory of relativity, and you can see that they match really closely. So this is kind of the first observational evidence that gravitational waves were a real thing. So as you saw in that first sort of like slinky thing, what happens as the wave passes by, if it's coming into the screen, it causes something that's a circle to compress in one dimension and expand in another, and then do the opposite as it passes by. So that's the motion of, if you had a ring, that's what would happen to the ring as the gravitational wave moves by. It's like a mechanical effect. So what some people realized was that this device, which is called a Michelson interferometer, and what this does is that it uses light to very precisely measure distances. So you have a laser beam, you split it at a beam splitter, the beam goes down two perpendicular arms, hits mirrors at the ends of those arms, and then comes back and is recombined at the beam splitter. And if these arms are exactly the same length, then no light goes to this exit port here. But if the lengths of the arms change a little bit, then a little bit of light will leak out. This is all due to interference of the light waves. And so you get a little bit of a signal at the output port. Yeah. It is very similar. Yeah, you're probably talking about the Michelson-Morley experiment. And yes, it's very similar detection principle or experimental principle. And in fact, that experiment is the one that led to Einstein coming up with the general theory of relativity. And so what he's referring to is an experiment that predated this one and predated Einstein's general theory of relativity, was an experiment that used a same kind of device as this to measure the speed of light in these two perpendicular directions. Because the thought was light must be traveling through some medium that permeates all of space, and that the Earth is traveling through this medium. So light must have a different speed in different directions relative to that, what they called the ether. But it turned out that it didn't. And so that was very peculiar. And then basically, after theorists thought about it for a while, it kind of culminated with Einstein's special theory of relativity and then his general theory of relativity that predicted the gravitational effects. So, but then you can imagine if you have this device and you put these mirrors on this ring, then when the gravitational wave comes by, it stretches and compresses the ring. Then it'll make these mirrors move, which will make this effect of the, sorry this is a little bit jerky, but it make the light leak out. And so you can basically use a laser Michelson interferometer like this to measure potentially the effect of gravitational wave passing through. The trick, though, is that the effect is very small. Gravitational waves cause things to move only by a very, very, very tiny amount. And so it's very hard to detect. So eventually, in order to see this very small effect, we had to make these very large instruments that basically amplify the effect of the gravitational wave. So that's where LIGO comes from. It stands for Laser Interferometer Gravitational Wave Observatory. And there are two of them. There's one in Washington State. This is eastern Washington, which is a desert. And then this is in the swamps of Louisiana. But the detectors are identical. And they both, once we got them working, we basically just leave them there, let them sit and record. We just record the signal of, the mirrors moving. And then we have, supercomputers essentially that are crunching all the data coming out of them and looking for a coincident signal between these two detectors. This is what it looks like inside this central building here. This is what it looks like inside there. So the whole thing is inside of a vacuum system because we have to shield that Michelson interferometer from any external effects. We have to shield it from the ground moving. We have to shield it from any air. Any air moving around could move the mirrors around, could look like a gravitational wave signal. So these tubes are where the laser beam is passing. So the laser starts over here. It goes and hits a beam splitter, which is in this chamber, goes down that arm, goes down this arm. The light comes back, gets recombined, and then we detect it in a photodetector over here. To isolate the mirrors from the ground motion, we suspend them. So this is the mirror here, and it's got a cover on it right now to protect it. But it's on a whole chain. It's hanging by these tiny little glass fibers from this mirror, which is hanging from more masses up from the top here, which is a big seismic isolation platform. And the point of all of this is to isolate this mirror from any motion, any external motion. Here's another view from inside the vacuum system, and this is from at the end of one of the arms. So this is the mirror that's at the very end of one of the arms. And so this, looking down here, is looking the 2.5 miles. I guess I didn't mention that these arms are 2.5 miles long here. So this is looking, that would be looking down the 2.5 miles toward the vertex. And here's the mirror at the end. And then this whole assembly here is to detect a little bit of light that leaks through this mirror. And we can detect that and get some diagnostics about what's happening to the light in the, inside the arm. So basically, LIGO is a transducer of space-time strain to electrical signals. So it basically is just, these mirrors are just sitting in space, the gravitational waves come by and they shake the space around, cause the mirrors to move, and then LIGO turns that motion into an electrical signal we record. That's where we look for our gravitational waves. So I like to say that LIGO is a space-time, which is actually pretty accurate in a lot of ways. So this is kind of the one technical plot I'll put up, but it kind of it pretty much says most of the story about how we characterize these instruments. And so what we look at here is we look at this is the signal coming out of the detector transformed into the frequency domain. So this is a little bit like looking at a spectrogram of an audio signal. Like, you know, you have like a graphic equalizer, right? Where you have the bass signals and the treble signals. That's kind of the same thing here. So you have the lower frequencies here, which would be like the bass signals, and the higher frequencies up here, which are like the treble. And so this is literally the spectrum of the noise that we measure. So it's like if you put a microphone into an empty room, right, with no sound, and you turn up the gain of the microphone, where you're trying to turn up to see if you hear any small sounds, eventually you'll start to hear a hiss, right? That hiss is just the noise of the microphone itself or of the amplifier. And that's what we're listening to here. This is the noise of the actual LIGO detector, just of its inherent noise. And that's what limits our ability to detect the gravitational waves, is that we have to get the noise that's inherent in the detector lower than the amplitude of the signal that we're trying to detect. It's exactly the same with a microphone, right? If you want to hear the sound of a pin drop, you have to have the microphone, the noise in the microphone has to be less than the amplitude of the noise of the pin dropping, right? And so this is we look at the spectrum of the noise so we can try to figure out what's going on at all the different frequencies. And so this black curve here is the measurement of the noise in the LIGO detectors at the beginning of our third observing run. So we've had 3 observing runs so far. The one that we're in right now started in April. And so this was the spectrum of the noise at that time. So a couple of things that I think are interesting to point out. One is that, look at the frequencies here. So 10 to the 1 is 10 hertz, 10 to the 2 is 100 hertz, and 10 to the 3 is 1,000 hertz. So what is your audio frequency band? What's the frequency with which you can, what's the frequency of sound waves that we can hear? Excuse me? Right. So 20 hertz is here, right? 20,000 hertz is higher here. But the point is that all of the signals that we're looking for are in the audio band. So you can actually listen. I can pull up a sound of it later, but I forgot to put it in my talk. But there, you can just listen to the sound that LIGO records directly. We can plug the output of LIGO directly into a speaker and just listen to the sound. And this just kind of sounds like white noise with a little bit of some like high-pitched ringing in it. And those ringing comes from these high frequencies up here, which are actually due to those glass fibers that hold the mirrors. Those vibrate. And we call them violin modes because they vibrate like a violin string. And you can hear that tone in the noise. So the other thing I'll point out is that this is what we measure. This black dashed curve is what we call our design sensitivity. So that's the level at which we think we should be able to get the detectors if we get everything all totally tuned up. But we're not quite there yet. We keep pushing down. So this light gray back here, this was in back what we call S6, which was in 2009. This slightly darker gray was from our 01. So we're in 03 now. And 01 was our first observing mode, which was back in 2015. And now we're down here. And we've gotten even a little bit better than this now. But these other colored curves show the things that ultimately limit what this noise level is. So the green one is seismic noise. So that means that's the ground moves, and even though we do all of this isolation of the mirrors, that ground motion still leaks through the seismic isolation system and moves the mirrors just a tiny bit. And so this green is the residual motion from the ground. This orange curve here, this straight line, that's actually thermal noise in the mirrors. Because the mirrors are not at absolute zero temperature, the molecules in the mirrors are moving around. They're bouncing around. And that actually causes a noise that we can pick up. I mean, these detectors are so sensitive that we can pick up the motion of the molecules in the mirrors themselves. And then this blue curve is what we call quantum noise. And again, we're so sensitive, we can actually pick up the quantum mechanical nature of light itself. So rather, you probably heard that light is both a particle and a wave. If you've heard of photons. So photons are the particles of light. And if you have a lot of light, you usually don't recognize that it's a quantum mechanical thing. But if you're very, very sensitive, you can pick up the individual photons. And so, for instance, down in these frequencies, the individual photons hit the mirrors at slightly different times. So they kind of like rain on the mirrors, which causes the mirrors to jiggle, just due to the random arrival time of the photons hitting the mirrors. And that actually causes motion of the mirrors, which is a noise. For us, is a noise. And then there's a similar effect at higher frequencies where the light hitting the detector has that same sort of rain effect. And so we have a slight uncertainty in when the light arrives at the detector, and that causes noise at these high frequencies. So we basically, all we're doing, the scientists that are building these detectors are basically just trying to figure out how to measure all of these technical noises and make them go away to get down to these, what we call the fundamental noises in the detectors. So the last thing I want to point out is that this what we're measuring over here, this is called strain. This is like the ultimate amount that the gravitational wave is bending the space. Over on this side is the same, it's the same axis, but this is in meters. So this is how much the mirrors are moving in meters. Okay? So at this frequency, at 100 hertz, the mirrors are moving by 2 times 10 to the minus 20 meters. So what is a millimeter is, how many meters is a millimeter? It's 1,000th. So 10 to the minus 3. 1 over 1,000, it's got 3 zeros on the bottom, so that's 10 to the minus 3. A micron, right, which is like the size of your hair, that's 10 to the minus 6. A nanometer is 10 to the minus 9. An atom, the diameter of an atom is about 10 to the minus 10 meters. This is 10 to the minus 20 meters. So this is 10 to the 10 times smaller than the size of an atom. So here's an atom, okay? We're going to zoom into the atom. In the middle of the atom, you have the nucleus, which is hydrogen. This is just made up of a single proton. Zoom into the size of the edge of the nucleus. That's the motion that we can measure with LIGO, with those giant 2-kilometer meters. We can measure the mirrors moving by a fraction of the diameter of the proton. I'll let that sink in. I've given this talk, I've worked on LIGO for a long time, and every time I talk about it, it blows my mind that we can do this. It's a really, really, really small number. I mean, that's why we're measuring, just the motion of the molecules in the mirror. We can detect the individual photons, because this thing is so sensitive, we can measure these tiny, tiny, tiny ripple, these tiny motion. And that's necessary because the gravitational waves are that small. So we had to make this whole thing this sensitive because that's the only way to detect these gravitational waves. So we started our first science run for what I guess I should say it's for advanced LIGO. We had an earlier incarnation of the instruments, which we improved, and we started detecting again in September 2015. And then on September 14th, when we were getting ready to run, and we were like doing what we're calling an engineering run, where we would basically try to fix things and let it sit for a while and then go back in and fix things. We're trying to get ready to just operate hands off for like 6 months. So during that time, we actually heard a really loud signal. So this was before we'd even turned it on really for the first time. We were just kind of getting ready. And we detected this signal. So if you kind of like you don't have to actually, this signal was so loud, it really surprised us how loud we had been preparing for these signals. We had made all this very fancy data analysis stuff to try to like sift through all of this noise to find this signal buried in the noise. And this signal was very loud. And if you just do some very simple filtering of the signal to get rid of some of the high and low frequency noise, you can actually see the signal in the noise, which is what is here. So this is what we actually measured in the Washington and the Louisiana detectors. And this is a numerical simulation of what two black holes colliding together with very particular mass. It's a numerical simulation of the signal that they would make, right? And then you can see what we did here is we just took this signal, literally just subtracted this signal away from it. This is just like very simple math. Take this signal, subtract this one, and then you're just left with noise, just random noise. This is not how we do the detection, but it's basically an illustration to show that what we detected here exactly corresponds to this numerical simulation we had made about the sound that two black holes would make if they collided together. And so this is what that signal looks like in the time and in the frequency space. So you can see that as time goes on, it starts at like 30 hertz at this like low rumble, and then by the time it gets loud here, it's up at like, almost 500 hertz, and it sounds like whoop. And I can play some songs later if you want. But basically, this was a really big deal, and this was the first ever detection of these gravitational waves, and it was a really big deal. We were all very happy. So I'll just point out really quickly, the way that we actually do the data analysis, the way that we look for these signals, there's a lot of ways that we do it, but we do these numerical simulations to create these waveforms about what the signals that we think we would detect would sound like. And then we just literally look for these signals in the data. So we do numerical simulations, create these waveforms for a lot of different types of black holes colliding together. And then on supercomputers, we basically just take these waveforms and run it along the data and see if we have a match. And we just do that over and over and over and over again. And we do it all the time. We're doing it right now, and we do it in real time. So this is another simulation of that same event. So these are two black holes as they would appear in front of like a star field, basically just like the Milky Way. And so what you're seeing here is this is all the warping of space-time around the black holes, because the black holes warps are really dense, and so they warp the space-time around them, and then they cause the light that would be coming from behind them to be bent. And so that's all of this warping you're seeing. If you take these black holes away, then you would just see a static star field. But because their black holes are moving around each other, they're causing all this crazy warping and bending of the light, which causes all this distortion. And then, they eventually coalesce together, and that's when they emit all of these waves that we can detect. So we kept observing. We heard a couple more. We took the machines down. We did some more improvements on them. We fixed them up. We made them a little bit more sensitive. And then in August 17th of 2017, so this was like 2 years later, we detected another event which was different than the previous ones. It was a lot longer. It was also very loud. It was a lot longer. And so we have, at this point, we have all of these analysis pipelines on these computers that are crunching the data as soon as we take it, right? We take the output of the detectors, we record the data, we digitize it, and then we send it to a computer cluster right away, where we have all of these processes that take these simulated waveforms and then look in the data for waveforms that look like that. And we can get an alert that one of these automated search pipelines has found something within like 5 minutes. So we've been trying to get that time down shorter and shorter, because what happened is we made this detection and we sent out an alert to astronomers. And we said, hey, we think we just heard a gravitational wave, and we think we know where it came from in the sky. And right at the same time we sent out that alert, this other collaboration called Fermi sent out an alert that they heard a GRB, which is a gamma ray burst, which is a big, it's basically just a burst of gamma rays. Totally different than LIGO, right? LIGO's hearing these waves of gravity that you can only hear with these LIGO detectors. Gamma ray bursts are electromagnetic waves. They're like a totally different physical phenomenon. And you hear that this was from a satellite that was in space that's just listening for gamma rays. And so right after we heard our thing, they sent out an alert that said that they saw something also. And so here's an example of how this new thing was so different, right? Here's the first detection we made. It was really short. This next one we made, these were all detections that we made previously, right? This was in 2015, 1509, 14, so that's the date, right? 15, 10, 12, so this was October 12th of that same year. December 26th, this was January 4th. August 14th, so this was 3 days before that. And see how these are all relatively short. These are all black holes colliding with each other, right? But this new one is totally different. It's really long, super long. It lasts like almost a minute. So it's a different kind of thing. And we heard this gamma ray burst. We got this alert from this gamma ray burst. And so what these are what we call sky maps. So this is, once we get a signal, we try to analyze where the signal in the sky would have come from, right? Where in the sky the signal would have come from. And so for the black holes, those were all detected just with the LIGO detectors. So they make these big sky maps where it's really hard to tell where it came from. But by the time we got to August of 2017, the European collaboration had come online, and they have a similar detector which is in Italy. And you can see that once they're online, these sky maps are much smaller. And so it's basically, again, to make the analogy to sound and microphones, right? If you have one ear, for instance, you can sort of tell where a sound is coming from. But it's much easier if you have two ears. You can start to localize where the sound is better. And if you have more ears, you can start to pinpoint very precisely where the sound is coming from. And that's the same thing here. We had two LIGO detectors, which we can sort of tell, but it's still kind of vague. But when the third one in Italy came online, then all of a sudden we can start to pinpoint much more precisely where the sounds are coming from. And so this was the first one with them, and then this little one is that 1717. And then I thought I had, oh yeah, here. And so then this is what happened is these were the three detectors, LIGO, the two LIGO detectors, and Virgo is the European one. We made these detections, we sent out alerts. Everybody got really excited because that meant that the astronomers may be able to point telescopes at that point in the sky and see something. Because we knew that what these were neutron stars colliding together instead of black holes. And neutron stars are made of exotic matter, but it's still, black holes are literally like holes in space. Light cannot escape them. Nothing can come out. So if two black holes collide together, they don't make an explosion that you can see because light can't escape from them, right? But neutron stars are like really hyperdense stars, but they haven't collapsed into a black hole yet. They're still made of matter that is sort of normal, relatively normal matter. And when they collide, they make a huge explosion. And we've predicted for a long time that two neutron stars colliding would cause gamma ray bursts and gravitational waves. And so when we saw those two things together, we were like, oh yeah, we've definitely heard two neutron stars colliding. And so basically every telescope on the whole planet started to point to this place in the sky. This was huge for astronomy. I mean, astronomers went apeshit about this. And so this is an example. So this is like a picture of the whole sky, and this is zooming in to where the event was. And I like this just because you get a sense of what it's like for modern astronomy nowadays, where like the sky is just so full of stars, and they can zoom in to this tiny, 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 tiny fraction of the sky to localize. You know, they can just zoom in. I mean, they keep going, going, going. And eventually, it zooms into this galaxy, which is 40 million light years away. And then on the edge of the galaxy, there's a little tiny spot. And they saw that. And that caused astronomers to just lose it. It was like the biggest that little blip was like the biggest discovery in astronomy in 50 years. Because we had seen people have seen these gamma ray bursts, but never been able to take a picture of them with a telescope, right? You could only see them with these gamma ray detectors, but they don't really tell you where on the sky they came from. And because we had these new gravitational wave detectors, we were able to hear it and figure out where on the sky it came from, which allowed the telescopes to point at it and take a picture. And it was huge. So that was very, very cool. Right around this time, I should point out, the guys who founded LIGO got the Nobel Prize in physics for the detection of gravitational waves. So this was all happening very quickly in the last couple of years, all this very exciting stuff. So this was, as of the beginning of this third observing run, which we're in now, this was all the black holes, the detections that we had. So here are all the black holes that were, where you have two black holes that collide together and make a bigger one. And then this was the two neutron stars that collided together. And there's a question mark here because we don't know if when they collided together, if they turned into a bigger neutron star or if they actually turned into a black hole. So that's just still a mystery to us. But this shows all of the other black holes and neutron stars that we know about that are sort of what we call low mass. But these purple ones are black holes that were detected by with sort of traditional astronomy, with electromagnetic astronomy, looking for stuff falling into the black hole, which gets accelerated and then emits like X-rays and stuff like that. And then these are neutron stars that we've seen in telescopes, but we've never seen two neutron stars collide together before. But that's what we did at this 1708-17. All right, and so then we have this worldwide network that we're building up to try to get more detectors, to try to localize better, to try to be able to hear more events. So we've got the two detectors in the US. The Virgo, this is kind of old, it's not under construction, it's completely built now. We have what we're calling LIGO India. So we have joined forces with India to build another identical detector to what we have in the middle of India. And then the Japanese are also building a detector under a mountain in Japan. And they're supposed to come online later this year, hopefully, or early next year. So to just summarize the LIGO part, we already have in 03, which I haven't talked about, we've already got dozens more detectors. Like every time we improve, so here's kind of an interesting thing. How we measure, with one detector, we can measure what we call its in-spiral range, which is how far away we can measure one of these neutron stars colliding, right? But that detector exists in the universe, and there's no preferred direction. So we think that, you know, these black hole collisions and these neutron star collisions are happening in any direction. So if we can hear them from some distance away, what we're actually probing is a whole volume in space, right? Just take that distance and make a sphere. And so everything in that sphere. So that's the size of that volume is the cube of the distance. And so as we improve the detector a little bit, the number of events that we can detect improves as the cube of that. So whereas we had 2 detectors in our detections in our first observing run, in our second observing run we had 10, and in this third observing run we've already almost had like 40. So the number of events just keeps going up as we keep improving the detectors. And we expect that when we get to that design sensitivity, we'll have, you know, basically a detection every couple of days. And so we're already starting to work on the next generation of these detectors, which are going to have more laser power. We're trying to reduce all this quantum noise with this thing we call vacuum squeezing. We're going to get better mirrors with better coatings. We're going to cool the mirrors to try to reduce those vibrations of the molecules in the mirrors. Better seismic isolation. If we make the longer we make the arms, the more sensitive the detector is. So we're trying to make a proposal to make a detector with 40-kilometer arms. So that's 25-mile long arms. And then they're already starting to build a detector that's going to go in space. And the arms in space are going to be 1 million miles long. And that's going to be 3 satellites in a triangle that are going to all be shooting lasers between them. And that whole constellation of satellites is going to be basically in the same orbit as the Earth, like trailing. It's going to be orbiting the sun. It's not going to be orbiting the Earth. It's going to be orbiting the sun in the same orbit that the Earth is. But anyway, once these new detectors come online, which will probably be in our lifetime, we'll be able to hear these neutron stars colliding, those things that have the really long signal. We'll be able to start hearing them years before they actually merge, right? So you remember that really long signal? That was the neutron star that made the gamma ray burst that we had telescopes take pictures of. And if we can detect, if we make our sensitivity better, we can detect those things even years before they collide. And then we'll be able to say, hey, if you look over there, you'll be able to see a gamma ray burst in 2 years. That'll probably happen in the not too distant future. We already can detect these black holes that we're detecting are already billions of light years away. And the universe is only 14 billion years old. So we're already detecting black holes about 1/10 of the way to the edge of the universe. And with these detectors with the 25-mile long arms, we'll probably be able to detect them out to like 10 billion light years away, which is basically to the edge of the universe. We'll be able to detect essentially every black hole collision that happens in the universe, which is crazy. And then the thing that I'm kind of really excited about is that we hear something that we haven't anticipated. All that we've heard right now are things that we basically predicted. We predicted that we would hear these black holes collide. We predicted that we would hear neutron stars collide. But we haven't heard anything yet that we don't know what the heck it was. So I'm pretty excited about that. So now I just wanted to talk a little bit about computing in LIGO to try to like bring it all back around. Please feel free to at any point ask any questions you want about anything that's in the past, whatever. But I mean, this is sort of an obvious statement since computers do everything in the world now. We use computers all over the place in LIGO. And in fact, when LIGO first started to be built in the 90s, and there were computers in the 90s, but there was still a debate when they were designing LIGO back in the late 80s about how much we needed to use computers. So there was actually some thought that, I'll come back to this in a minute. And I just want to say that Python, I don't know, does Python, anybody know Python? Python is awesome. We use Python all the time. Like, it is, in science, it's almost the de facto thing that everybody uses, and particularly in gravitational waves. I think more so in gravitational waves because our field is pretty new. So, you know, astronomers don't use Python so much, but astronomy is an old field. It's been around for a while. So they were using they were using tools that existed before Python was invented. But by the time the gravitational wave field was coming around, Python was around and everybody recognized how awesome Python was. And so people started to put a lot of like numerical analysis stuff in Python, scientific computing tools, and Python's obviously just like a good general purpose language. So we basically do almost everything in Python. I'm a huge fan of Python. So for instance, the detectors were designed, and the next generation of detectors are designed with a lot of computer simulations. So these are two projects that I've helped work on. This one is called PyGwink. It's because it's the Python version of something called Gwink, which existed for MATLAB before, but it's the gravitational wave interferometer noise calculator. And so it's basically that plot I showed of the frequency spectrum of LIGO with those curves, like this is the quantum noise and the seismic noise and the thermal noise. This program has analytical functions for calculating those noise sources given your parameters in your detector. So what we do is we do a lot of simulations with this, or like optimizations, where we'll pick some parameters for the detector, like how massive are the mirrors, or what is the reflectivity of the mirrors, or how powerful the laser is. We'll run it through this program Gwink, which calculates what the noise level is. And then from that noise level, we'll calculate how sensitive we would be to gravitational wave signal, to like a binary to neutron stars colliding. And then we'll vary those parameters and see if that improves our ability to detect the neutron stars. And so that way we can use this kind of optimization to pick the parameters for the detector, like what's the best mass to use. That's a little bit of a silly example because we know we would actually like to use the biggest masses we can use. But for some other things, some other parameters, we have to tune them to find out what's the best value for the parameters. We use all sorts of CAD. As you can imagine, we have crazy mechanical CAD files for the whole vacuum system, for all the mechanical components. We also have programs that calculate the optical signals, the laser signals in the detector. And that's hugely useful to know how the light is going to be affected by the mirrors moving and stuff like that. So this is something that I mean, all of these things are things that I work on a little bit. Like I work on this project a little bit, but the thing that I've been mostly, my primary job for the last couple of years has been with the digital control system for LIGO and the automation system. And well, I'll come back to that in a second. So this is basically a block diagram of the control system for LIGO. So this down here, what we call, when you do control theory, the thing that you're trying to control is called the plant. And this comes from old, kind of like old school industrial applications where literally the thing that they were trying to control was like a chemical process in a manufacturing plant. So the thing you're trying to control is called the plant. And in our case, our plant is the interferometer. And it's the mirrors and the laser beams bouncing between the mirrors. So we're trying to control the mirrors to keep them all very quiet and aligned and that sort of thing. So what we do is we have all of these signals that sensors that detect what's going on, a lot of light sensors, a lot of like motion sensors for the seismic isolation system. We have what are called field racks where we have the analog to digital converters. So we take the electrical signals coming from those sensors and we digitize them. And we feed those into computers, and that's what we call the real-time control. And so what we have running on these computers is just computer programs that essentially just look at the data coming in, do a really fast calculation, and then calculate a signal going out that would be, for instance, how much to push on one of the mirrors. So you take the signal from the photodetector, and you know where the photodetector is and what light signals it's seeing. You then calculate, based on the signal that you're seeing, how much you should push on the mirror to like cancel that signal out. So that all happens with these real-time pieces of software that run on these computers, and that's all Linux. I can talk in depth about any of this as you want. And then what we have on the top of this is we have what's called a message passing. Have you guys heard about message passing? What's a good example of message passing? Like, well, like, I mean, essentially like instant messaging. That's like a kind of an instant messaging where you have you send a little packet of data off that gets routed to some other computer, right? Where it's like if I send you a text message, that sends a packet that bounces through the computer network and then gets to somebody else's phone. And so we have this whole distributed message passing system here where computer software that's running up in this level. All of this is computers that are basically like in computer racks that are next to the instrument. And they can all talk to each other through this message passing system so that they can look at the data that's going on in this real-time system and inspect it, and then send messages back to that real-time system to tell it to change its state somehow, right? Like change the gain of how much it's going to push on a mirror. And so then up here we have a whole bunch of computer processes that are all kind of distributed. They're all processes that all run this low level. They all look at the signals that are in this real-time system, and they make decisions about how to feed back to change the real-time system. And then there's like a whole hierarchy of these things so that up at the very top, basically the operator of the interferometer will tell this guy, hey, lock the interferometer, get it ready for gravitational wave detection. And then this guy will tell a whole bunch of guys below him to do stuff that'll trickle on down to telling this fast real-time system what kind of, how it should change itself to move the mirrors around to get ready for detection. And then this is just an example of this kind of state machine graph that we use to represent all of the states that each of these processes could be in. And so basically what's happening is that it's moving around in the state graph to sort of like, this is just a simplified representation of the mind of that computer process, essentially. So we use GUIs, graphical user interfaces, for drawing these block diagrams of what the real-time system does. And then we turn those drawings into real-time code. So we have what's called a real-time code generator that generates real-time computer code that runs on the Linux operating system. That's this low level here. And then this distributed message passing system, which I was talking about, and then this automation system is called Guardian, which is the thing that works up here that kind of coordinates everything. And so then we also have all of the scientists, basically at the detectors, the work that the scientists are doing are looking at what's going on in the digital control system to try to understand what's happening in the interferometer. And then they're trying to improve the automation system, and then also trying to figure out what is causing the noise in the instrument and how we can fix it. And so we have a bunch of GUI tools for doing that. So this is a shot of the control room at the detector in Louisiana. And you can see just completely cover all of the walls with monitors and graphs. And this is the main one. And as you can see, this kind of looks like that plot I put in the middle of my presentation, the first half of my presentation. And that's because that's exactly what it is. This is exactly that same plot with the same frequency range of like 10 hertz down here and 1,000 hertz up here. It's literally the same plot. And you can see it's front and center because that's what we're looking at all the time to tell us how good the instrument is doing. It's basically how loud is the noise in the instrument right now. And then these are all just time series plots, like these here, telling us what's happening to like the power levels of the laser in different parts of the instrument, or like how much is the seismic isolation system moving around. And if you could see this wall over here, we have plots of the how much the ground is moving, of like, are there earthquakes and stuff like that? Because if there's an earthquake comes, it shakes everything, we can't detect. These are camera views of the laser spots in the detector. And so we can see the like laser beam flashing, and if the beam is changing shape, that's all giving us information about what's going on in the instrument. Here, this is actually that automation system I was talking about. So these are screens that are telling us what the automation system is doing. And then we have these computer terminals all over the place where scientists sit, and you can see this is full of all of this. This is kind of old school graphical user interface, but this GUI that he's looking at here is telling him what's going on in that real-time control system, that Linux real-time control system. So he's basically got these GUIs where he's got buttons where you can push and change what's happening in that real-time system, and little dial indicators and stuff that'll tell it, like, you know, it's like a digital indicator of like what's the power level of a laser or something like that. And then we have all sorts of tools that do data analysis. So we can take the signal coming off of the instrument and like transform it into, you know, this plot is actually updating in real time. You know, if you were to look at a video, like this purple curve would probably be like moving up and down. And so we have all of these things. And then these guys almost always have some sort of interactive computing environment open. So either like MATLAB or Python. Has anybody used IPython, interactive Python, or Python notebooks? These are basically ways that they're interactive Python terminals where you can type in Python commands, or MATLAB has this very similar thing, where you can type in commands to you know, basically get data, plot it, change the plots, that sort of thing. And so that's pretty much what they're doing all the time, is looking at all of these signals to try to see what's going on in the instrument. And then, you know, finally, the actual data analysis process is a whole huge computing thing. We have big computer clusters that are at each of the two sites, and we have a really big cluster that's at Caltech. And so we get those clusters, particularly the one at Caltech, gets the data from all of the instruments, from the two LIGO detectors and from the detector in Europe, and soon to be the detector in Japan, brings them all to this computer cluster where those analysis programs that I was talking about earlier that look at those simulated waveforms and try to find those signals, they're running on big computer clusters with like 1,000 computer nodes. And you can actually, we actually can just log into these computer clusters and run these like interactive terminals to do like little analysis things. But most of it's all running automated now. So people write the computer code to do this analysis, to like read in one of these numerical simulations, compare it to data that we just took from the instrument, and then see how well they match. That's all been automated now. So we have, you know, just all of these processes just run automated, and we just watch the results come out. And then, yeah, like I said, we do these numerical simulations. So these numerical simulations are also done on big computer clusters. These numerical simulations are much more sophisticated computer programs than our searches are, actually. Our searches are actually fairly simple, right? Because all you need to, I mean, it's more complicated in practice, but really all that it's doing is you have a computer program that's running, that's reading the data that just came off of the instrument, it's reading the numerical simulated data, and it's doing a comparison. And it's saying, is there a signal there, yes or no? If not, move on to the next thing. So that's pretty simple. And it's easy to parallelize, right? You can take 1,000 computers, each with 64 cores, and so you can run, 64,000 of these things in parallel, to each one comparing against a different simulated waveform. But to actually calculate what these waveforms are, they're doing full numerical simulations of Einstein's equations for black holes. So they're taking a black hole and solving Einstein's equation to figure out how much the space-time would be bending. And that's actually, those equations are really hard to solve. You can't just like do it math and paper and write down a solution. They're so complicated, you have to do this numerical simulation where you basically, simulate the black holes colliding and then see what the output is. So that's a big thing. And then machine learning is, we're physicists, we're not computer scientists, so tend to be kind of behind the curve on all of these things. So we're definitely doing a lot of machine learning stuff, but I wouldn't say we were on the forefront of machine learning. And so we don't actually use that much machine learning in our day-to-day operation right now, but that's changing rapidly because we're all starting to learn all of these algorithms and starting to learn what they can do and realizing the ways that we can improve our analysis, the ways that we can, we haven't done any machine learning, we haven't done any sort of like AI for the control of the instruments yet, because that's very complicated. And we only have, these instruments are big and expensive, and we don't have very many of them, right? We've only got 2. The thing that, like, for Google to train something to like recognize a picture of a cat, they can give a supercomputer a bazillion pictures of cats and tell it to learn how to do that. So in order for us to do something similar, to like tell a computer how to detect gravitational waves with our instrument, we either have to have basically a perfect simulation of our instrument, which we don't have, because that is as time consuming as making the actual instrument, really, or we would have to have extra of these instruments. And this is, this is why we don't have automated cars yet, because it's much easier. We will have them sooner than we will have machine learning finding gravitational waves. But they still have to have either a full simulation of a car, or they have to actually go drive a car around. And with a simulation, you can do it a lot faster, right? Like the reason, like AlphaGo could learn how to play Go because it's not limited by playing somebody in real time. They can train it on playing itself, sped up as fast as they can make it go. But we can't do that here. And with a real car, you can't like just speed up time and like see how it's going to do and do it over and over again a bazillion times. So it's actually, practically speaking, machine learning is really useful in some domains where you can do things really fast, where you can do simulations really fast. But if you can't do a simulation fast, then machine learning is not really going to help you that much. And that's what we're kind of struggling with. So, but we're still using it for a lot of other stuff. And then here's some links to stuff. So this is our main website. This is the LIGO Open Science Center, where you can go here and get actually on the web one of these interactive Python sessions, just like what the scientists use in the control room, where you can make plots of the actual data from LIGO detectors. You can take those simulated signals and sort of like pretend like you're doing a search. You can basically get demos of the algorithms we use for the searches at this site. This is the database where we store all of our events. So you can go there right now and see a list of all of the events that we have released publicly, that we have had public alerts about in our third science run that we haven't even published. We haven't published them yet, but you can see our public alerts about them. And then this is all of the simulations of those black holes. The simulation of the black holes that I showed earlier, that was made by this collaboration called Simulating Extreme Spacetimes. And they do those numerical simulations that I was talking about and make really cool graphics from those. So you can see their simulations there. That's it.